Hi everyone, my name is Satvik of Branch Computer Science and Engineering, Section C, roll number 20951A05G4. The topic which I got for concept video for the subject Applied Physics is different techniques of fabricating PN junction. First, let us talk about general introduction to fabrication techniques of a PN junction diode. If you see this diagram carefully, upward there will be a slow rotation of rod and there will be a seed placed in this point, and this part is made up of high purity silicon monocrystalline, and the gap between this is covered through inert gas or a vacuum, and this is made of low purity silicon polycrystalline. This holds the lower support clamp, and this is a quartz container. There will be the downward movement of induction coils every time. Downward movement of molten region along with impurities is done here. In practice, the PN junction is formed from a single monocrystalline structure by adding carefully controlled amounts of donor and acceptor impurities. Here, discussion is limited only to equitation with the basic techniques and terminology, not expertise in fabrication. The first and foremost requirement is to obtain an extremely rare germanium or silicon impurity of less than 1 part in 10 billion is required for most semiconductor device fabrication today. For obtaining pure semiconductor material, it is first purified chemically for reducing the impurities further and to ensure the formation of a monocrystalline structure. A technique known as flattening zone is quite often employed. The monocrystalline structure is formed through the use of a small seed of semiconductor, example silicon or germanium. The seed itself is a monocrystalline that has been very carefully cut along the face of its cube latex. Support clamps are employed to hold the purity of polycrystalline. The rod, seed, and support clamps are placed in a quartz cylinder. The process may be carried out in a vacuum or by surrounding the semiconductor with an inert gas. Great care is required to ensure that the semiconductor is not further contaminated during the floating zone process. Induction coils encompass the quartz container as shown in the figure. The coils are excited by a radio frequency voltage. The circulating currents are induced in the semiconductor due to the magnetic field set up by the RF currents flowing through the induction coils. The heat so produced melts the zone which is exposed to it. As a result, a molten region is formed. Slow rotation of rod makes the semiconductor atoms to align themselves with the atoms in the monocrystalline seed. Thus, an induction coil are moved downward. The molten region follows and a monocrystalline structure continues to grow from the seed. Purification of the semiconductor rod occurs simultaneously with the formation of the monocrystal. The impurities in the semiconductor rod tend to become more liquid than the semiconductor. Thus, in induction coils are moved downward. The impurities tend to follow the molten region. Once the induction coils have traversed the length of the semiconductor rod, the impurities are collected in its lower end. The lower end of the semiconductor rod may then be cut off, and the process is repeated until the desired impurity level is attained. Once a pure monocrystalline semiconductor has been produced, carefully controlled amount of donor and acceptor impurities are added to the semiconductor without disturbing the orderly monocrystalline structure. Thus, a PN junction is. Let us talk about semidiodes are normally one of the following types. Grown junction diode, Li type or diffused junction diode, diffused junction diode, epiphytic grown or planar diffused diode, point contact diode, grown junction diode. Diodes of this type are formed during the crystalline pulling process. P and N type of impurities can be alternately added to the molten semiconductor material in the crucible, which results in a PN junction, as shown when a crystal is pulled after slicing. The larger area device can then be cut off into a larger number, say in thousands, of small area semiconductor diodes. Through such diodes, because of larger area, are capable of handling large currents, but larger area are also introduces more capacitive efforts, which are undesirable. Such diodes are used for low frequency alloy type or fused junction diode. Such a diode is formed by first placing a p-type impurity, a tiny pellet or aluminium or some other p-type impurity, into the surface of an n-type crystal and heating the two until liquefaction occurs where the two materials meet. An alloy will result that on cooling will give a p-n junction at the boundary of the alloy substrate. Similarly, an n-type impurity may be placed into the surface of a p-type crystal and the two are heated until liquefaction occurs. Alloy type diodes have a high current rating and large PIV, peak inverse voltage rating. The junction capacitance is also large due to the large junction area. If you look at this figure, here comes the crystalline pulling rod and here is the seed and this is the PN junction. And the slicing process is done like this. Aluminium or indium pellet is placed here above the n-type substrate and the cathode, and this is the p region and the anode. Alloy type or fused junction diode. Diffused junction diode. Diffusion is a process by which a heavy concentration of particles diffuse into a surrounding region of lower concentration. The main difference between the diffuse and alloy process is the fact that liquefaction is not reached in the diffusion process. In the diffusion process, heat is applied only to increase the activity of elements involved. For formation of such diodes, either solid or gaseous diffusion process can be employed. The process of solid diffusion starts with the formation of layer of an acceptor impurity on an n-type substrate and heating the two until the impurity diffuses into a substrate to form the p-type layer as illustrated in the figure. A large p-n junction is divided into parts by cutting process. Metallic contacts are made for connecting anode and cathode leads. In this process of gaseous diffusion, instead of layer formation of an acceptor impurity, an n-type substrate is placed in a gaseous atmosphere of acceptor impurities and then heated. The impurities diffuses into the substrate to form p-type layer on the n-type substrate. Through the diffusion process requires more time than the alloy process, but it is relatively inexpensive and can be very accurately controlled. The diffusion technique leads itself to the simultaneous fabrication of many hundreds of diodes on one small disk of semiconductor material and is most commonly used in the manufacture of semiconductor diodes. This technique is also used in the production of transistors and ICs, integrated circuits. If you look at the figure of solid diffusion and gaseous diffusion, here comes the painted indium n-type substrate and indium scraped off. The cutting process is done like this. In gaseous diffusion, gaseous atmosphere containing indium particles are in n-type substrate and the cutting process is done like this, which is same as solid diffusion. Epitaxial growth or planar diffuser diode. The term epitaxial is derived from Latin terms epi means upon and taxis meaning arrangement. To construct an epitaxially grown diode, a very thin single crystal high purity layer of semiconductor material, silicon or germanium, is grown on a heavily doped substrate base of the same material. This complete structure then forms the N region on which P region is diffused. SiO2 layer is thermally grown on the top surface, photo-etched and the aluminum contact is made to the P region. A metallic layer at the bottom of the substrate forms the cathode to which lead is attached. This process is usually employed in the fabrication of IC. If you look at the figure of epitaxially grown or planar diffuser diode, there is an anode in a metallic layer, and this is the SO2 layer, SiO2 layer, and this is the p-type and n-type epitaxial layer, substrate, and a metallic layer below which is a cathode. Point contact diode. It consists of n-type germanium or silicon wafer about 12.5 mm square by 0.5 mm thick, one face of which is soldered to a metallic base by radio frequency heating, and the other face has a phosphor, bronze, or tungsten spring pressed against it. A barrier layer is formed round the point contact by a push pulsating current forming process. This causes a P region to be formed around the wire, and since pure germanium is n-type, a very small p-n junction is in the shape of a hemisphere is formed around the point contact. The forming process cannot be controlled with precision. Because of small area of the junction, point contact diode can be used to rectify only very small currents of the order of mA. On the other hand, the shunting capacitance of point contact diodes are very valuable in equipment operating at super high frequencies, as high as 25,000 milli. If you look at the figure, it consists of a glass envelope and a germanium and a metallic ring which is attached by a tungsten wire spring and an anode lead. Most semiconductor devices contains at least one junction between p-type and n-type material. These p-n junctions are fundamental to the performance of a function, such as rectification and switching in electronic circuit. Here, the discussion is about how the p-n junction diodes are made. The technology of junction fabrication is a broad subject which includes the accumulated knowledge and experience of many research and manufacturing groups forming junctions and making contacts to them in mounting suitable for device. Basic materials, chemicals, and equipments for the process are silicon wafer, the Tempest diffusion furnace, oxygen and nitrogen gas, bubbler, boron nitrate cakes, deionized water plant, chemicals, a diamond cutter, masks, ultrasonic vibrator, the vacuum coating unit, and a mask aligner, shortest spinner and baking furnace, temperature controlled heater, voltmeter and ammeter, and other essential items. Some other general purpose things is required such as tweezer, safety goggles, covering dress for lab E, and thank you.